All right, good afternoon. Here we are again for another lovely session of ENGR 2302 Engineering Dynamics. So today we're going to talk about material from chapter 14 of the text, of the Beer Vector Mechanics text, and this will be over systems of particles. So let's see, that is, we are recording, we are good to go, and that should do it. So again, we'll be looking at systems of particles. So again, just let's do a brief introduction here. We'll be looking at systems of particles. Systems of particles, which is our collection of particles all traveling together or having some relationship to each other. Can be bound or unbound, etc. So looking at systems of particles. So we're still not considering yet rigid bodies. We're still looking at particles that themselves have no depth or mass, or not mass, no dimensions. But we're looking at how a system of them behaves together. Then I need to define something called effective force. Effective force. So effective force, the effective force of a particle force on a particle, of a particle or on a particle, is defined as the product of its mass and acceleration. So regardless of the actual forces on the individual particles, for a system of particles or a collection of particles, I'm saying that the effective force is whatever the mass and acceleration of the center of mass of that particle system is. That will be the effective force. Mass times acceleration. That will be the effective force on that system of particles. So also, we will see that the system of external forces, or the collection of external forces, the system of external forces acting on a system of particles, So the system of external forces, just a few terms we need to look at. So we'll have systems of particles and system of forces acting on a system of particles will be equivalent to the effective forces. Will be equivalent to the effective force on the system. Will be, actually I should say equipolant, and we'll see what that means. EQUIPOLLENT. Equipolant with the system of effective forces, system of effective forces on the system. The system of effective forces on the system. Let's see, yeah, effective forces on the system. Oh, sorry. On the system. And so we will also look at mass center, or center of mass, mass center of a system, and we will look at the implications above and implications of the above. So this is what we want to cover in chapter 14. Of the above. All right, so moving on. All right, let's move along. Let's see. So let us look at Newton's second law. Second law in a group setting or a system setting for a group of particles. For each particle, let's say each particle pi, where p is going to be a particle, pi in a system of n particles. So consider, let's look at Newton's second law. So I want to look at Newton's second law for each particle pi in a system of n particles. In a system of n particles. So here, in other words, let's look at let's look at this and say, okay, well, okay, so let's say we'll have this relationship here. Fi vector, and I'll define each of these in a moment, plus summation from j equals 1 to n for Fij. Fij is equal to miai, or also the force here. If I look at the rotation, if I'm looking at rotation here, so this is force, and this is next line will be rotation. Moments, we might say. So this is translation, rotation, or forces and moments. Ri cross Fi plus the summation of j equals 1 to n of Ri, or sorry, Rj, or sorry, no, Ri, can't make up my mind, Ri cross Fij is equal to Ri cross miai. miai. And where all of these things, what do these mean? Well, Fi here, I'm going to let Fi be an external force on a particle. So this is not this is describing multiple forces on one particle if they do exist. So basically, capital Fi is one of possibly many external forces on a particle. So capital Fi is an external force on a particle, and lowercase Fij, and I will draw this out, I'm just getting the math in first, is going to be the internal forces. Something like gravity would be an example of an internal force. Something generated inside the body of a particle, or inside by the particle's own mass or something. Something like this. And then miai is the effective force. So, again, at capital Fi, it will be an external force, lowercase Fij will be an internal force, and miai will be the effective force, mass times acceleration. And so, fundamentally what I'm saying here is, if I draw this out graphically, if I have a system here, and again, I'm just considering some arbitrary particle pi, and then let us say we have something like this here, and Let's just do this in red here. So actually first I will label the displacement vector from the center, the initial position vector, Rij. Rij, this will be used for your moments, or sorry, yeah, Rij, or just Ri, I guess in that case. No, sorry, just Ri, if I can get my labels proper. Ri, and then I could have Fi here. This would be an external force on the particle, Fi, and then maybe an internal force, Fij, lowercase Fij here. And then maybe I have another particle here, and I'm going to label another particle over here, maybe particle J, and that really illustrates what we mean by an internal force. So maybe I call this one particle J. So Fij would be an example of would be like an internal force, something like gravitational attraction between the particles, something like electrical attraction or repulsion between particles. It is an internal force generated within the swarm of particles. That here, so and any external force in the particle plus any internal force in the particle will then thus be equal to the equivalent external force on the particle, which would just be Ri. We still have the initial vector position, but I'm just saying whatever acceleration happens to undergo, that will be the equivalent. That will be the equivalent external force. So I would have Pi here, Pi, and then the equivalent external force, MIAI. And they have subscripts i's and j's and things like that because we would be doing summations using summation notation. And then MIAI here. So basically the vector sum of all of the external forces and plus the vector sum of any internal forces on a particle will be equal to the effective external force. Okay. So, looking at that, moving on here, and actually let me finish my arrows here, that would be nice. Let me do that here. So, moving on, I can also say that the system, so that was on an individual particle, also, this is still an individual particle. The system of external and internal forces and internal forces forces on a particle is equivalent to the effective force on a particle, just like we described by this. When I say it's equivalent, we mean that it would generate the same momentum, same change in energy, all this kind of thing. Is equivalent to the effective force on the particle. Effective force on the particle. And also the system of external, the combination or the system of all the forces acting on a system of particles is equivalent to the effective force on the system. So just like we had an equivalent force on an individual particle, we can also say we have an equivalent net force on the swarm of particles as a whole. Equivalent to the effective force on is equivalent to the system of effective forces. Is acting on a system of particles is equivalent to the effective force. The effective forces. Okay? So, in other words, if I have a, let me kind of draw this out. Let us say we had, I don't know, I'll draw maybe 3 particles, or maybe just, yeah, I'll draw 3 particles or something like that. So, let's say we had several particles. Maybe I have I, Pi, Pj, and then just some other random particle here that would be some number between I and j. We could have internal forces between these. First, each of these particles would have their own position, Ri and Rj, here, Ri and Rj. And then I could have a series of internal forces. All of these particles could generate internal forces between each other, be they gravity, that kind of thing. So Rij here, and then another set of internal forces here, another set of internal forces here. So as you add more things, this can obviously get more and more complicated. Then I could have an external force maybe on particle I, an external force, and I could have multiple external forces on each particle if I wanted. External force in particle J, etc. But then I'm going to say that this is equivalent to the equivalent force on the system as a whole. So something like this, or the system of equivalent forces is probably, it would be a better way to state it right now. Is equivalent to the system of equivalent forces. So the overall set of forces is equivalent to the system of equivalent forces, where imagine we had a whole bunch of equivalent M1, MI, AI, etc. So I used green over here, let me use green over here. So if I have these 3 particles, well then each of these would have their own equivalent forces based on their masses and accelerations, and equivalent torques, all of that good stuff. And so you'd have a MI, AI, etc. for each of these. And the overall system would be the effect of all of these forces on the system as a whole would be equivalent to the effect of all of these reduced forces or combined forces on the system as a whole. All right, so now let's apply, let's continue looking at this. Continue applying Newton's second law to these. So then here, if I sum all of the elements, if I do a summation over all elements, or all the particles, actually all the elements including forces, so the summation of I equals 1, and don't worry, we will actually get some examples of what all this nonsense means, but don't worry, we'll get there. We got to go through some theory first, though. I equals 1 to n of Fi plus the summation from I equals 1 to n times the summation of j equals 1 to n of all of the internal forces. So we're going to look at the summation of all the external forces plus the summation of all of the internal forces is equal to the summation of the effective forces. I equals 1 to n of the effective forces on all the particles, and all these are vector sums, of course, not algebraic sums. MI/AI here. And we can also look at this in terms of moments. So, if I look at this in terms of moments, I equals 1 to n of Ri cross Fi plus the moments generated by any internal forces. I equals 1 to n summation of j from 1 to n times, or not times, of Ri crossed into Fij is equal to the summation from I equals 1 to n of the moments generated by all of the internal all of the effective forces on each particle of Ri crossed into Mi Ai. Crossed into Mi Ai. And then, so I could draw this out again. Oh, let's see. So, in other words, I can reduce this and also say here. Actually, let me continue going through the theory again. Since the internal forces, so if we see that so I can actually sort of eliminate the internal forces from this equation by saying, since the internal forces occur in equal and opposite pairs, since if we're looking at the center of mass of the system as a whole or something like that, occur in equal and opposite pairs, they will disappear from our equation. In equal and opposite pairs, the resultant is 0 on the system as a whole. The resultant is 0 on the entire system. So internal forces can generate a force on an individual particle or an individual small body, but they cannot change, say, the center of mass of the entire system or the moment on the system or something like that. Only an outside body can do that. Their resultant is 0. They drop out of the equation. So then I could simply say the summation of forces from I equals 1 to n is equal to the summation of the equivalent forces on each particle, which makes sense, hopefully. And also I could do the same thing for the torques, or for the moments, depending on the perspective. Ri crossed into Fi is equal to the moments generated by all of the equivalent forces. Ri crossed into Mi Ai. So what I mean by that, we'll give an example of what I mean by the internal forces canceling out. So once you get that here. So if I show you, for example, think of a really complex object, like I don't know, any object, any macroscopic object, actually. Like if you have say my cat. My cat is a complex system. So yes, I'm going to draw my cat. My cat is a collection of particles, a rather fluffy collection of particles, and then I'm going to draw a poorly rendered cat. So here is my poorly rendered cat. And at a fundamental level, my cat is a very complex system of particles, right? I'm sure she would appreciate being referred to as a system of particles, but she is a system of particles, and we could consider ourselves a system of particles if we wanted to as well. I need to draw the cat very carefully. So there is this cat, and the cat could be represented as a system of countless quadrillions of particles, right? Each of them generating a variety of internal forces against each other, right? And each particle interacting with every other particle, both electrically and to a minor degree gravitationally, but primarily electrically, right? Unless we got down to the subatomic scale, we were saying the individual subatomic particles that are making up my cat are interacting through nuclear forces as well, the strong and weak nuclear force, etc. Although if we really wanted to do that, I should probably name my cat Schrödinger or something like that, Schrödinger. Anyway, but primarily the particles that make up my cat are interacting electrically. Now, if my cat jumps up from the ground to the printer where she likes to sleep, she likes to sleep on top of, we have this big laser printer at home, and she likes to sleep on top of it because it's warm. She also likes to sleep on top of things like computers and other electronic devices that we just collectively refer to as cat warmers. So she likes to do that. But anyway, if I were to model my cat jumping off against the ground, and I am going to do a very poor job of my cat jumping. I really cannot draw a cat, so you'd think I could, being a cat person. Looks like a little demon or something. Here's my happy cat. Well, anyway, jumping. And I want to model how this cat jumps through the air. I don't need to consider all those countless of quintillion. Actually, that would be an interesting number of forces. If you added up the number of atoms in the cat and then realized that every one of those is generating a force, electrical force against every other particle, that would be an absurd number of forces, wouldn't it? So, but all I really need to consider is the center of mass of the cat and the normal force against the cat's paws against the ground, and also the weight of the cat, right? That's all I need to consider. I only need to consider the external forces that are the cat interacting with any other body. The actual internal forces, the effectively infinite number of internal forces representing the cat and holding the cat together, do not figure into the system, because the motion of the system, simply because they all cancel each other out. They're all occurring in force pairs. They're going to cancel each other out, etc. In a system that's more easy to understand, let us consider something like the Earth and the Moon going around the Sun. So if I have the Earth and the Moon, there are two main internal forces that occur between them, namely the gravity between them, the Earth and the Moon. Each generates via the law of universal gravitation. They exert a gravitational force that is quite large on each other. Now, we could also talk about tides and things like that, and deformation of the bodies, but let's just talk about a simple one and look at the raw gravitational force. We could actually calculate this if we wished, and in fact, you've done some homework problems like that. So we could do that there, but so they're gonna generate an internal force. Well, if I consider them as an isolated system, I would maybe not consider that an internal force. I would consider each as their own internal forces. But if I wanted to model the motion of the Earth and the Moon around the Sun, well then, if I had the Sun down here, not to scale, them combined would have a center of mass, something like this, and they would have a net force, a larger force between the Earth-Moon system and the Sun. And I would define this as the external force and the gravity between the Earth and the Moon as an internal force. If I wanted to model the motion of the combined system, the center of mass of the combined system around the Sun, I would not need to consider the gravity between the Moon and the Earth, because that's a combined system. So that's an internal force. That cancels itself out in the case of the Earth-Moon system. So I could consider a very complex system like the cat, or a very simplified system like the Earth-Moon orbiting system. But in either case, internal forces will cancel each other out. Let's see what's next. Also, if I wanted, so that's hopefully makes sense. So that would be able to reduce to, again, I could then say the system of external forces and the system of effective forces are equipolant but not equivalent. So here, something like this. What do I mean by that? Well, generally what I'm saying by that is that they will generate the same potential, equipolant. They will generate any kind of same potential energy, momentum, etc. But they're not necessarily exactly the same, because I could break them down and look at the individual motions of particles. They would be a little bit different if I looked at them. They're not exactly equivalent, but they are equipolant in terms of the system as a whole. So that is a good definition of equipolant we might be able to work with here, etc. So let's move on. Let us look perhaps next at linear and angular momentum in terms of the system here. Let's see. So let us look at, I want to move on to talking about linear and angular momentum of a system of particles. So today's lecture is going to be very theory heavy, unfortunately, but there's a lot to get through. Linear and angular momentum of a system. Linear and angular momentum of a system. So, the linear momentum of a system of particles, let's first look at linear momentum. Linear momentum. Of a system of particles. Well, this is going to be using capital L for our linear momentum is equal to the summation of I equals 1 to n, or n, of MIVI. So this is the vector sum of all of these. Or L here, L dot, the rate of change in angular momentum, or sorry, linear momentum, is the summation of I equals 1 to n of mi vi dot, which is equal to the summation of I equals 1 to n of mi ai. The masses times the acceleration. And from this, I can also say that the resultant of the external forces is equal to the rate of change, just very similar to what we've seen before, to the rate of change so the resultant of external forces is equal to the rate of change in linear momentum. The linear momentum of a system. Momentum of the system of particles. Of the system of particles. So, or this could just collapse to the summation of forces is equal to L dot. Like that, like so. And also I want to look at the angular momentum in the same way, about a fixed point, for instance. So the angular momentum about a fixed point O of a system of particles angular momentum about a fixed point O of a system of particles. So let's analyze that. Well, we've used capital H for angular momentum before, so I'm going to say H sub O is equal to the summation from I equals 1 to n of Ri, basically the moments, or sorry, the cost products of Ri cross MIVI. We'll get some moments later. MIVI, that is your angular momentum, Or the rate of change in angular momentum for a system of particles is equal to the summation from I equals 1 to n of, I need a dot here. The rate of change in angular momentum is equal to, no, that is a really bad summation sign, summation of, here I could go Ri dot plus MIVI plus the summation of I equals 1 to n of Ri crossed into MIVI dot. So this one deals with this term deals with a changing position, a changing r vector. This one deals with a changing velocity vector. So this is a changing linear velocity. If this one is a changing linear velocity, this is a changing radius, or a changing position, we could say. Sorry, what? This one here? Okay. Oh, sorry. Yeah, you're right. Sorry, that should be a cross product. Sorry about that. Is that what you're wondering? Yeah, sorry about that. Little typo there. Sorry about that. I just can't write. Crossed into, yes. If you ever make a typo or something like that, feel free to correct me. I am, as we have seen, I am definitely not, despite popular opinion perhaps, or actually definitely not despite popular opinion, I am not infallible. So, anyway, and this would then be equal to the summation from I equals 1 to n, 1 to n of Ri cross Mi Ai. Here, or just basically saying the rate of change in angular momentum is equal to the summation of all of the individual positions crossed in to the mass times accelerations. And in a similar vein, just like I did previously, I can say the resultant moment about fixed point O, a fixed point O, of the external forces is equivalent to the rate of change in angular momentum. Is equivalent to the rate of change of angular momentum. So the summation of MO, the summation where this is meant to be a capital M if you can't read my poor writing, capital MO equals to the rate of change. That's the moments, the summation of the moments on a system of particles is equivalent to the rate of change of the angular momentum of the system. All right, so let's keep going then. Maybe a bit more before we take a break. Yeah, I think we'll get through a bit more here. I want to look at the motion and rotation of the mass center, or the angular momentum about the mass center of the system of particles. Okay, got that? Okay, so again, I want to look at the mass center. I will define what I mean by the mass center, and then we'll look at how the mass center of a particle, or a system of particles, allows us to effectively consider a swarm of particles effectively as one object or one system of particles. And you notice we're kind of I don't know if you can kind of get the feel for this, but we're kind of building up to rigid bodies. We started looking at individual particles, then we looked at looked at individual particles, the translation of individual particles, kinetics, kinematics, that sort of thing. Then we started looking at momentum, energy, all of those methods, again, of individual particles. Now we're looking at swarms of discrete particles, and eventually we'll be working our way up to continuous rigid bodies. So now let us look at the motion of the mass center of a system of particles. Motion of the mass center of a system of particles. So the motion of a mass center, in other words, we would have to find the motion of the mass center, we would need to consult a geological table or geological database and find the rate of motion in the Italian continental plate. That makes sense? That's the rate of motion of the Vatican, which is the mass center. Oh, never mind. That was a long way for that really bad joke. Get it? Mass center. Oh boy. Yep. I worked really hard on that one. Spent 3 days coming up with that. That's what I was doing all spring break. So anyway, I'm going to define mass center G. Let us consider mass center G, capital G, G of a system of particles, is defined by position vector RG. So we'll have some mass center, and with a position vector RG, which satisfies this here, which satisfies MRG is equal to the summation I equals 1 to N of MI/RI. In other words, the equivalent system forces, the combined system of forces on the system of particles as a whole will be equivalent to the, if all of the mass were lumped at that point, if all of the combined mass of the system of particles were lumped together into a single particle at that location, that would be the mass center. And if it were equivalent, if it behaved in the same way or underwent the same acceleration, that is what we mean by the equivalent mass center. So then let's take that and do the derivative here. So let's actually, this is defining it. So this is mathematically defining what the mass center is. It is basically saying that the mass center is a position, it's a location. There may not actually be anything at that position, but the position. So really, all that the mass center means is a position, a point in space, and that point in space is equivalent. If I multiply the mass times that position vector, that would be equivalent to the overall MI/RI. In other words, what we're talking about is almost the centroid of the system. Remember centroids from earlier in statics class? We're looking at the centroid, the mass centroid of the system. So if I take that and then differentiate twice, so if I take the derivative of this twice, the first derivative, I would get m r dot g is equal to the summation I equals 1 to n of mi ri dot. Then I could also say this is equal to m vg, because the time derivative of position is velocity, is equal to the summation, again, I equals 1 to n of mi vi. And I know from earlier that this is equal to the angular momentum, which is equal to the angular momentum. And if I take the derivative of this, I can get that m ag is equal to L dot, the rate of change in angular momentum, which is equal to simply the summation of forces. So, in other words, so this is just taken directly from, this comes directly from taking the time derivative of the equation for the centroid of a system of particles. So, the mass center moves as if the entire mass and all external forces, entire mass and all external forces were concentrated at that point. Now, this may seem technically complex and may seem difficult, but you've already to a certain degree been doing something like this. So in your previous problems where we worked through things of like the motions of orbits and that kind of thing, you considered, say, even something like the Earth as a point particle, didn't you? You considered even something like the motion of the Earth, motion of the moon, satellites, whatever, as just the satellite would be a point particle, the moon would be a point particle. You compressed the entire mass of the Earth into a singularity, into a black hole or something like that, treated it all like a single point particle, and analyzed its motion that way. You didn't worry about body deformation or anything like that. You treat it like a point particle, and you can do the same thing here. This is all we're doing. In fact, let's see. In fact, now that I've defined the angular motion of the motion of this, let us, I think, take a short break, and we'll come back and look at this some more.